Alright, I think I'm going to record these in two little blats since no one showed up to recitation yet. I started recording some things based off of questions I had in email. So the first question is Chapter 1, Section 7, Question 15b. And it's a proof. And most of the questions I've been getting have been around proofs. And so this asks, we're going to let A be an n by n symmetric matrix. So we'll let A be an n by n symmetric matrix. Then our definition of symmetric, that means A equals A transpose. And we're going to need part A. So part A says show or prove that A squared is symmetric. And the book does a nice little proof on this. So we'll start with does a nice little proof that leads up to this. So we'll let A and B be symmetric matrices. Now we know matrix multiplication does not necessarily commute. So what we're going to say then is A times B, does A times B, is this symmetric? Is A times B symmetric? So to show this, we have to show that A, B transpose equals A times B. That would be the definition of symmetry. It has to equal its transpose directly. Now, what we can do is we have the relationship AB transpose is B transpose A transpose. So I'll just go focus on the left-hand side here. And since these are symmetric matrices, so by definition of symmetric, A equals A transpose and B equals B transpose. So this becomes B times A because these are symmetric matrices. And this is only true if the multiplication AB commutes. So that's kind of, and your book does this kind of at the end of Theorem 1.7.2 or somewhere around there. It does an example of the transposes of symmetric matrices. And then it just kind of makes this that symmetric matrices, the product of symmetric matrices, are not necessarily symmetric. But that works really nice for us because now we can go, well, A squared is A times A. And now we can use this argument here, right? We can replace B with A. And so AA equals AA. So A squared is symmetric. Right, if we use this definition of when the product of symmetric matrices will be symmetric, then we can prove that A squared is symmetric. And that works really well because the question that I had was on part B. So part B asks, when does 2 is 2A squared minus 3A plus I symmetric? And this is where we have to use 1.7.2 as our guidelines here. I think the book has most of the proofs between the exercises and yeah, between the exercises. And it's worth reading what's around 1.7.2 in the book. Fortunately, my electronic copy does not have page numbers on it. I apologize. So I'm talking about Theorem 1.72. Theorem 1.72 says A transpose is symmetric. If A is symmetric, then A transpose is symmetric. That falls naturally out of the definition. Then A plus B and A minus B are symmetric. And C, KA is symmetric. And so we notice we have an addition here, or a collection of terms. So if I can prove each of these terms is symmetric, then I can use this to show that the whole output is symmetric. So first off, is I symmetric? Alright, so any identity matrix is 1 across the diagonals and 0 everywhere else. Well, if I look at any row, that's equivalent to its column. You get 1 followed by zeros. And so if I switch my rows or columns, I transpose does equal I. So I is symmetric, so we know this part is symmetric. A is given to be symmetric, and so K times A is symmetric, so that's symmetric. And we just proved A squared was symmetric, so K times A squared is symmetric. So we have each part being symmetric, and so by part B, this polynomial, this matrix polynomial is symmetric. So 2A squared minus 3A plus I is symmetric. And that works us through those. All right, like I said, I'm going to record this in parts because I'm going to look at a little bit larger proof from chapter 2 that uses some cofactors.